Welcome everyone. So in the last class we have started our discussion on high power charging or DC fast chargers, where we have seen that we require less amount of charging time so that the vehicle downtime can be reduced to 10 to 15 minutes from 0 to full charge. So for those type of applications where we require faster charging rate, so we will be requiring high power converters. We have seen various levels of charging and their classifications, types of conductors available with us and their layouts. Then in this lecture we will continue with the discussion of converters which will be suitable for very high power chargers or DC fast chargers. So as I say DC fast chargers, so there will be having two stages of conversion. First will be our AC to DC conversion, then there will be an DC to DC converter. So first we will start our discussion on multi-level AC to DC conversion. So this will be perfectly bidirectional converter. So what is the meaning of that? The power can flow from DC side to the AC side or from AC side to DC side based on the control technique used and the reference set to us. So the same converter can be used to develop our multi-level DC to DC converters. So we will see those also after we are done with the discussion with the AC to DC conversions. So the first example of our multi-level converter is diode-clamped multilevel converter, which is shown over here. So why the name is called as diode-clamped? So if you see the circuit configuration, here we have various diodes which are connected in the circuit to clamp the voltage. So what is the meaning of clamping? So the voltage at a particular point of the circuit would be fixed because of the diodes. For example, this is the node 2. So here if you see, this potential is fixed at VDC by 4 with respect to the ground. Normally this neutral point which is marked as N is our ground potential or the reference potential terminal. So this will be generally grounded. So from with respect to this point, the potential of our node 2 is fixed at VDC by 4. Similarly, the potential of node 1 is fixed at and 50% of the DC link voltage, that is the maximum AC voltage this converter can generate. So we will see why the output voltage will be restricted to VDC by 2. Similarly, when we see this node 3, its potential is fixed by this diode at an value of minus VDC by 4 with respect to the neutral point. So why this, when I say why this is fixed at this point, so whenever I will be turning on the corresponding switch, I will see that this point will be connected at the output and the potential of this capacitor will be applied across the output terminal. So because of the presence of diode, we are able to fix the potential of particular nodes at a particular point. So that's why we say that to be an clamped diode clamped circuit, and we are using diodes to clamp the voltage. So it is a diode clamped multi-level converter. So here as an example we have considered an 5-level diode clamp circuit. Okay, so similarly we can consider higher number of levels as per the voltage requirement. So more will be the voltage, more will be the levels, so that we will not require series connection of our devices. So what limitations we get from the series connection of the devices? The switching frequency will be very much limited when we have series connection of devices, because the dynamic characteristics or the switching characteristics will be different. So because of that we generally try to avoid series connection of devices. So here the voltage rating increases. So we will see after the discussion that the voltage rating of each of the devices will not be equal to the DC link voltage as it was for our 2-level converter. In 2-level converter, the rating of the switch was equal to the entire DC link voltage. Here it will be something different. That is what we will see after the analysis of the switching states of this converter. So here we are considering a 5-level converter. So there will be 2 into m minus 1 switches in the converter. So what is the meaning in this? We have an per phase leg shown over here. So in this now we are considering m to be 5. So it will be giving me m minus 1. So it will be 4 into 2. So it will be total of 8 number of devices. If you count, we have S1 to S4 and S11 to S41. Okay. So we have 8 number of devices as we have considered 5-level diode clamp circuit. Now this DC bus is split into n minus 1 different potentials by using the capacitor. So if you see n minus 1, so here m is 5, so it is equal to 4. So if you see we have 4 capacitors, C1, C2, C3 and C4, and they are used to split the DC link voltage as they are connected in series. So the entire link voltage, DC link voltage will be equal to VDC, and each of these capacitors, as 4 of them are in series, they will be sharing an potential which will be VDC by 4. So, here for 5 level, this will be the 4 voltages for different voltage levels, including 0 stage. Okay. So, that is why we say this as an 5 level converter. So, what is the meaning of number of 5 level converter, 7 level converter? It is representing the number of discrete voltage steps it can produce at the output AC voltage, that is across the VA terminals. So, here in this, when I go for implementing this converter in practical application, I will see that it will produce 5 different voltage levels at VA. So, why we are interested in increasing the levels? First is we will be avoiding the series connection of devices. Second is more is the number of steps, more will be the waveforms sinusoidal nature, and our THD will be decreasing. Our aim was to generate a perfect sine wave. So, if we have an higher number of levels, so our THD will be decreasing. But the cost which we have to pay is more is the number of levels, more will be the device count in these circuits. Okay. Now, diode clamps the output at to a common DC point. Okay. So, clamping diodes hold the output voltage at the intermediate DC bus terminal voltage and limits the voltage across each switch to VDC by M-1. As in our initial discussion, I said that rating of the switch will be different than the DC link voltage. So, this is how it will be defined. So, in this case, as we have an M equal to 5 or 5 level converter. So, each device has to block only VDC by 4. So, what is the meaning of that? If I have an 1 kV device, suppose, and we are not considering any type of margin of safety or derating factor. So, in that case, if I have 1 kV, so the DC link voltage in our 2 level converter gets restricted to 1 kV itself. We cannot have more than 1 kV, or else I have to go for series connection of devices. Now, in this case, if I use the same device, that is 1 kV device, now this is VDC by 4 will become equal to 1 kV. So, now I can have an DC link which is equal to 4 kV. So, based on the device and the available DC link or the desirable DC link, we can calculate the number of levels. And M level NPC will be having N-1 DC bus capacitors and clamping diodes per phase. Okay. So, if you see what will be the number, it is 4 into 3, that is 12. Okay. But in this figure, if you see, we have only 6 diodes. Okay. So, why this difference is there? So, if you see what will be the potential across this diode, if suppose for some combination I turn on S1, S2 and S3. Okay. So, I have turned on S1 and S2, S3 for some switching combination, suppose. So, this point, this node will be connected to the top bus, and at that same time, if these 3 are on, the 4th one will also be on. Okay. So, why this will be the switching combinations, we will see that in the next slide. So, here this point will get connected to the bottom bus. So, what will the voltage across D13? It will be equal to this capacitor voltage. But what will happen to D3 now? D3, this node is connected to the top bus. So, it will be connected across all the 3 capacitors, that is C1, C2, C3. The voltage across C1, C2, C3 will be applied across diode D3. So, what is the meaning of that? Now, diode D3 will not be a single diode, but it has to contain series connection of 3 diodes. Okay. If I assume that the voltage rating of the diodes which are used in this circuit have same value or same voltage rating. Okay. So, from that factor, this number has come into picture. Similarly, here we will have 2 diodes in series, and here in this case we will have 3 diodes over here and 1 diode over here. So, in each diode leg, if you see, we have 4 number of diodes, 3 diodes, 1 diode over here, 3 diodes over here, 2 and 2, 3 over here, sorry 1 over here and 3 over here. So, each leg has 4 diodes. So, it will be giving us 12 number of diodes for this single phase of the circuit. So, now we have seen the number of devices and number of diodes, number of capacitors required by this circuit. Now, let us see what will be the operation of this circuit. Okay. Suppose this is the switching combination table where the status of the switches are given over here. Okay. So, if you see the numbers, they are written as S1 and S11. So, why they are written in that way? So, because of an particular states or particular combination of their operation, that is they will be operated in the complementary manner. So, what is the meaning of complementary manner? If this switch is on, it is obvious that the switch will be off, and vice versa condition. Okay. So, when I have pair of devices where one switching pulse is complementary to the other one, I say that these two switches are complementary pair of devices. Okay. So, here S11 and our S1, they will be complementary to each other. If you see, wherever this S1 is on, S11 is off, whenever it is off, my S11 is on. Okay. So, from this discussion we can see that S1 and S11 are complementary, S21 and S2 are complementary, S3 and S31, and so as for S4 and S41. Okay. So, all of them will be, or we have 4 set of complementary pairs. Now, let us see how they will be switched. So, if you see in this case, all the upper switches are on, that is S1 to S4 are 1. So, what is the meaning of that? These 4 devices are having the gate pulse S1 to S4, they are having the gate pulse. So, point A will be connected to the top bus and VA will be equal to VDC by 2. That is what is written over here. So, what is VA? It is the potential between the VA and the neutral point. So, in this case, if you see, if I connect and load in between these two terminals A and N, so I will see that this point is connected to the top bus and the neutral point is over here. So, it will be experiencing the voltage which is applied across C1 and C2 capacitor, which is equal to VDC by 2. So, it will be plus VDC by 2 when this switching combination is activated. Now, second combination where I have removed the gate pulse from S1 or it has been turned off and we have given the pulse to S11. So, in this case what has happened? Now, S1 is off and this S11 is on and the remaining 3 switches are on, that is 2, 3 and 4 are on. So, what will happen now? This A point gets connected to this node. Okay. So, because these 3 switches are on. Okay. So, if the current is flowing in this direction, so this diode will be coming in the path and this will be the path of the current from the neutral point. It will flow through this and to the load and back to neutral point. So, if the current is negative, it will flow through the lower path. Okay. So, irrespective of the direction of current, as this is an voltage source converter, irrespective of the direction of current, my voltage will be predetermined based on the switching state. Okay. So, here also when the current is positive, it flows through this. If my current is negative, that is it is flowing from this side. So, it will flow through this and to the neutral point and back to the ground. Okay. So, from node 2 it will go to the ground. So, in this way, whether the current is positive or negative, in both the cases what will be the voltage across this one? So, if you see this point and neutral. Okay. So, we have an resistance which is connected between this point and the neutral point. So, it is equal to VDC by 4, that is what is marked over here. Whether my current is positive or negative, my load will be experiencing an voltage which is equal to 1/4 of the DC link voltage when I have this switching combination applied across the converter. Okay. Now, the third combination when I want 0 voltage. So, what I have done, I have removed the pulse from S1 and S2 and I have turned on S3, S4 and S11 and S12. So, what is the meaning of that? This 3 and 4, 1 and 2 are connected. So, based on the current direction, what will happen now? This path D to this node will be connected to the output stage. Okay. So, neglecting the on state drop, I can say the A potential and this node potential will be the same for the switching combination, which is equal to the neutral point, because our load is connected between A and neutral. Now, both of them are connected together. So, the load will experience 0 voltage. Okay. Similarly, now the VDC by minus VDC by 4. Okay. So, for this combination what has been done? S4 is turned on, S11, S21 and S31 is turned on. Similarly, this node will be coming into picture and the load will be connected, these two nodes will be connected together and the load will be connected between neutral and this node. So, which will be giving us an voltage of VDC by 4, but in the reverse direction. If you see, now negative is being connected to this node, whereas in our previous cases the positive was connected across this node. Okay. So, this positive terminal was connected. So, we were getting positive voltage. Now, in this case we will get negative voltage, that is minus VDC by 4. Now, the last combination in which we have turned on all the 4 lower switches. and what will be the voltage? Midpoint is connected to the ground and we have the other terminal connected to the negative bus. So, we will get the maximum negative voltage, that is minus VDC by 2. Okay. So, what is our understanding from this switching combination? So, we have 4 complementary pair of devices in an 5 level converter. If I have 7 level converter, then I will have 6 complementary pair of devices and so on. So, here we have 4 complementary pair of devices, and the maximum voltage which can be generated by this converter is equal to plus VDC by 2, and we have steps that are 5 different steps, that is plus and minus VDC by 2, plus and minus VDC by 4 and 0. So, that is why we call that as an 5 level diode clamp circuit. And here we have seen the number of devices and the ratings of those, that will be equal to VDC by m minus 1. So, in this case it is equal to 5 minus 1, so VDC by 4. So, each of this device has to block only 1/4 of the DC link voltage. So, if I want to increase the DC link voltage further, I have to go for higher number of levels. So, the rating of each of the device will be decreasing. So, I will not require any series connection of devices. So, what are the advantages of this circuit? So, this has single DC source requirement. So, I can have a common DC source, that is related to VDC, and from that I can generate an AC waveform which will be having m number of steps, where we have considered 5 level converter as an example. Okay. So, now reduce harmonic content compared to the 2 level inverters. Why? We have multi-level waveform now. So, now we wanted a sine wave over here. Now, we will be getting various steps. So, the THD will be less in this case compared to our 2 level converter, where it was switching between 0 and your VDC, whereas in this case it can generate intermediate steps. So, we can minimize the error between the sine wave and the generator waveform. So, our THD will be less. Smaller output filter requirement, because THD is less, so our filter requirement will be less. If we go for much higher number of levels, we will see that we will be eliminating the requirement of filters totally. So, well established and commercially mature technology, because these multi-level converters have been developed since a longer time and they are practically being used. So, now what are the limitation of this circuit? Okay, so we have seen the advantages. The limitations are number of clamping diodes and the devices, they will be growing quadratically as my device number of levels increases. Okay. So, the clamping diodes, so what is the meaning of that? We have seen the relation, it is given by m minus 1 into m minus 2. So, as my number of levels increases, so the number of clamping diodes or the devices required over here will be increasing quadratically. Okay. So, I will be requiring much higher number of devices if I am going for higher number of levels. So, that is what is the limitation of this circuit. Capacitor voltage balancing is difficult. So, as in our analysis, why we have got this intermediate steps, that is plus or minus VDC by 4, and we have got the peak values at plus and minus VDC by 2. So, those are dependent on this capacitor voltage. The intermediate step, suppose this capacitor is not charged to VDC by 4, it is having some other voltage. So, we will get some other voltage, because this point will be connected to the output, and whatever is the voltage across C2, that will be applied across it. So, when we go for actual working of this, when we have actual loading of this converter, we will see that these capacitors will not be balanced, because we do not have any redundant combination in the circuit. So, what is the redundant combination? For a given output voltage level, if I have multiple combinations which can be used, then I say the circuit has redundant combination, whereas in this case for a particular voltage level we have particular switching combination. So, because of that, the capacitor voltages will be diverging from each other, and we will see that we will require additional mechanisms to balance these capacitor voltages. So, unequal loss distribution, the duty ratio of the switches or the conduction time of the switches will be different for different output voltages, and they will not be balanced uniform. That what is the meaning of that? The time duration for which my suppose S1 is conducting, the S2 will not be conducting for the same time. So, the loss will be different. Hard to extend between 3 to 5 level in the practical use, because of this increment of your bus capacitors and the divergence in the voltage. Now, medium voltage applications. So, in this industrial drives, where this will be used. So, this is used in pump, fan and mill type of loads. Then traction, so railway traction and metro propulsion converters, in that also we see the application of this Diode-Clamped converter. Wind energy back to back conversion. So in the wind energy we have also discussed while discussing our renewable energy. Wind will be generating a variable frequency AC. So now we have to convert it into fixed frequency AC. So we will be having a back to back conversion system which will change the variable frequency AC to DC, then from DC to fixed AC. Then active front end rectifier and STATCOMs. So these are another application of this converter. Active front end converter which we have seen while discussing our chargers. Then our HVDC applications where we want not very high voltage. So there we can go for this VSC based diode clamp circuits. Then the next variant. So in the diode clamp circuit we have seen that the capacitors across the bus were not balanced because we do not had any redundant combination. To address this issue, we have one more solution, that is the clamping diodes are replaced by your flying capacitors. So what is the meaning of that? So if you see, instead of the diodes, here we have various capacitors. Okay. So why we say this flying capacitors? Because their potentials are not fixed, they are floating capacitors. Okay. So floating, it means they are not connected to steep voltage point. So what is the meaning of that? This point was fixed to neutral point. But if you see, the capacitors are not connected to this fixed point. So they are floating in nature, or their potential is variable and depends on the algorithm which we use and balance the voltages. Okay. So that is why we say that as flying capacitors. Then each flying capacitor is pre-charged to a fraction of DC link voltage. So how these voltages are calculated, we will see that in the next switching combination. So for M level flying capacitor, it needs M minus 1 into M minus 2 by 2 number of flying capacitors per phase and M minus 1 DC bus capacitors. Okay. So these are the DC bus capacitors which is same as that of our previous circuit where we had M minus 1 for M number of output voltage levels. Here we require, instead of this diodes, if you see, we require and capacitors which is having quadratic relation, which is M minus 1 into M minus 2 by 2 in this case. Okay. So now the switching operations of this converter. Okay. So if we see now, here also we have the same 4 set of complementary states. So here only 4 switching combinations are required. So written over here. So what is the understanding? Wherever it is marked as 0, the complementary switch will be off and vice versa. So in this case, now if I have CF1, so I have first applied this 4 switching pulses, that is S1 to S4 are on. So VA is getting connected to the top bus, and in this case if you see, what will the potential across the output? It will be equal to plus VDC by 2. And when I have the other switching combination, that is I am turning on S1, S2 and S3. So S4 is off, and what will be the potential, how the conduction path will be there. So if you see, first combination, in this combination which we have considered, the status is required as NC and plus. So what is the meaning of this NC? No change, that is the capacitor is not in the conduction path, that is the meaning of NC. So if the current is not flowing through the capacitor, it will not get charged or discharged. So the capacitor voltage will be maintained as it is. So that is why we say that is no change. Whereas in this combination, if you see, we have NC and we have an plus over here. So what is the meaning of this one? So if my current is positive, okay, so in this case my CF3 capacitor, what is the CF3 capacitor? This capacitor. Okay. So the current will come from the bus, it will flow through this and it will flow through the diode and it will go out. Okay. So if I see what is happening to the current, so it is entering the positive terminal of the capacitor CF3. So if my current is positive, my CF3 will get charged. And what is the status of the other two capacitors? They are not in the conduction path, so their voltage will not change. So similarly, if you see the same VDC by 4 voltage, okay, so how we have got this VDC by 4 voltage? So if you see, only the C4 voltage is appearing and the CF3, that is CF3 capacitor is being inserted in the path and it is charged to VDC by 4. So this is my neutral point. If I measure the potential of VA with respect to this neutral point, so it will be subtracted VDC by, if I apply KVL in this loop, I will see minus VDC by 4 and plus VDC by 4 plus VAN is equal to 0. So, when I take it on the other side, I will get plus VDC by 4 as the output voltage. Okay. And the capacitor is getting charged if the current is positive. So, that is what is marked over here. Everything over here plus and minus, they are written with respect to the positive direction of current. If the direction of current is negative, the opposite thing will happen. Okay. Now, let us see the next combination, which is giving the same output voltage, that is I have turned on S1, S2 and S4, S1, S2 and S4. Okay. So, in this case what has happened, now suppose the current is positive, it is flowing in this direction in the same way of analysis, and this switch is off. So, it has to go through this capacitor, then it will flow through this diode, through this capacitor and to the output stage. Okay. So, now if you see which capacitor has come into the path, both CF2 and CF3 has come into path. CF1 is bypass, so that is why it is marked as no change. Now, let us see which is charging and which is discharging. So, we have marked this positive direction of current. If you see, the current is entering the positive terminal of the capacitor CF2, so it will be behaving as a load and it will get charged, whereas the current is entering the negative terminal or leaving the positive terminal. So, it will behave as a source and it will get discharged. So, that is what is marked over here, plus and minus. Okay. What will be my output voltage? Again, if I apply KVL between these two nodes, again I will see that my output voltage will be equal to plus VDC by 4 for this combination. So, now in these two combinations I have got the same voltage. So, I say this to be an redundant combination. Similarly, we have two other combinations also, which will also give me the VDC by 4. So, I have 4 switching combinations which is giving me VDC by 4 voltage. So, what advantage I get in this case? So, if you see, based on the status of the capacitor voltage, I can select any particular combination. Okay. Suppose I want a switching combination which will my CF3 voltage is undercharged, I want to charge it, the current direction is positive. So, I will select this combination. So, I will select this combination when my CF3 voltage is less than its nominal voltage and I will charge it. Similarly, if I want to charge CF2 and CF3 discharge CF3, in that case I will apply this combination too, and so on. So, based on the capacitor voltage and the output voltage requirement, I will decide which particular combination can be used such that the capacitor voltage can be balanced. Okay. So, we will stop at this point. So, what we have seen today? Today we have seen multi-level converters which will be used in our charging applications to develop specifically our DC fast chargers. So, there we have seen our first diode clamp circuit, which required a quadratic increment of your clamping diodes, and it had a limitation of the balancing of the capacitor voltages connected across the DC bus because there was no redundant combination. Then we have seen flying capacitor, where we have various floating capacitors in place of the clamping diodes in our previous circuit. So, here the advantage which we have got is it has various redundant combinations which will be giving us the same voltage combination which we have seen for our VDC by 4. There we have 4 combinations. So, I can select any one of them to balance out this capacitor voltages. So, it addresses the limitation of divergence of the capacitor voltages and requirement of additional mechanism to balance the voltage, as in the case of diode clamp, is eliminated in our flying capacitor based circuit. Okay. So, we will continue from this point in the next class. Thank you.